Welcome to lesson 3 of unit 5. So we're still looking at rational functions and analyzing them. So the key thing here is that a rational function is defined as any sort of equation where we have a function in the numerator and the denominator can't be 0. So characteristic 1, as we saw in our last lesson, is non-permissible values for x. This is always going to be looking at your denominator and saying that we cannot divide by 0. Okay? So we then need to decide, is it an asymptote or a whole? But it's always, again, based on denominator cannot be 0. So when we look at this first one, we see that our non-permissible value is going to be set, so 0 cannot be x minus 3 times x plus 3, or plus 1 rather. So when we factored, learning about polynomials in grade 11, when we talked about this in our polynomials unit in grade 12, we always look at this and we see, okay, anything multiplying by something else to equal 0 means that one of those things had to be 0. So we can break it apart just like that and say that, well, x minus 3 can't be 0, and x minus 1, or plus 1, cannot be 0. From here we can see that x cannot be positive 3, and again that plus sign is not necessary, or minus 1. So those would be my non-permissible values. I then look and see, okay, would either of these factors in my denominator cancel out with my numerator? And the answer is no, because I've got different signs for my 3, so nothing cancels out, because it would have to be this whole piece, because multiplication comes before subtraction and addition. So nothing cancels, therefore these would both be asymptotes. For example 2, we'd set the denominator so that it cannot be equal to 0. And again, you can put the 0 before or after, it doesn't really matter. So x cannot be 3. That's great. But this time, if I look at my numerator versus my denominator, I'm multiplying by x minus 3, and I've got x minus 3 in the denominator, so they cancel out to be 1, or just not important. So when I actually look at what this would end up being, I would end up graphing y equals x plus 1, but then I'd have a whole at x equals 3. Again, that's because it doesn't show up in the simplified version of my equation, but it is in the original version of the equation. So wholes happen when pieces cancel. Example 3. In this particular case, I can factor my denominator because I notice that this is a difference of squares. We've talked about those before. So 0 cannot be equal to, and then it would be 2 minus x, 2 plus x. And so x cannot equal plus or minus 2. Because my numerator is just an x squared, there's no actual constant in there. I'm not going to be able to cancel out either of these pieces. I can't just do this. That's not allowed because this x is subtracting by something else in the denominator prior to that division taking place. The implied brackets that are around that kind of stop me from being able to cancel those out. So these are my non-permissible values, positive and negative 2. And because they don't cancel, these are going to be asymptotes. My fourth example, again, I look at my numerator and I'm like, oh, well, I can factor that. So if I look at this, I've got x, and again, it's a difference of squares. X plus 5 and x minus 5 all over x plus 5. So my non-permissible value piece stays the same. So x cannot be, and you might be able to spot it over time. X cannot be -5. When I look at my numerator versus my denominator, and so this is why factoring both the numerator and the denominator is important, because I look and I see that actually it cancels out with part of my numerator, which might not have been obvious given the original statement of the equation. So when I go to graph this, I would graph y equals x minus 5, so just a straight line, but then I would have a hole at x equals -5, because that value is not allowed in my original function. My second characteristic is looking at horizontal and oblique asymptotes. So this comes into play when I look at the degree of the expression in the numerator compared to the degree of the expression in the denominator. So this first example, we see the degree of the expression in the numerator is less than the degree in the denominator. So as x approaches infinity, y approaches 0. So we get a horizontal asymptote as y equals 0. So as we get bigger and bigger and bigger in the denominator, my numerator doesn't actually change at all. And so I'm dividing 4 by bigger and bigger numbers. That's getting closer and closer to 0. Okay, so we see that in the form of, and this is negative, so I'd expect a reflection from my original graph. So it looks something like this. Whereas usually it's supposed to be in quadrants 1 and 3, it would be in quadrants 2 and 4 because of that negative out in front. Okay, so that's what we would expect. So horizontal asymptote at y equals 0, vertical asymptote at y, or sorry, that is not right. I should find my non-permissible values. Should be -4, so it should be shifted over here. Again, I'm just sketching, so this is a rough outline. Okay, when we look at the second example, first of all, I can talk about my non-permissible value being that x cannot be 1. So automatically I know that there's a non-permissible value there. It doesn't cancel, so there's no helping me. Okay. Now the tricky part here is that when we're dealing with this, we can divide it out evenly, so it actually goes in 2 times, and it leaves me with 1 over my denominator, because that's the remainder again. And that's where the negative comes from also. Because that first part comes in as a constant, because they matched the same degree, we would look at this graph and say, okay, well, as x approaches infinity, this also approaches 0. So y minus 2, or y would be 2 minus 0, or just 2. So that's where I would expect my horizontal asymptote. So this one's kind of a little bit convoluted, that idea that you need to divide out your denominator to try and simplify this as much as possible in a one that maybe it's not so obvious that you can simplify because there's no factoring and canceling. Okay, so again, we use synthetic division to simplify. And that will help us determine our horizontal asymptote. Okay. So again, the key thing here would then be to look at our remainder. and then we would plug it back in to our equation. And so then we plug it back in to our simplified equation, and that tells us our horizontal asymptote for the whole graph. So it tells us it's a positive 2. This is a degree of 1, and so I would expect my shape to be something like this. Okay. Example 3, in this case we have a greater degree in the numerator than we do in the denominator. Degree in numerator is greater than degree expression in the denominator. So we are still going to use synthetic division. And we're going to actually do the same approach. So we get our new kind of quotient or expression, excuse me, here. And then we write the remainder as a fraction. Again, we're then going to determine the horizontal asymptote of the remainder. And then we would plug it in. So in this case, we get y equal into simplified equation. So plugging in 0 here leaves us with x minus 1, and so that tells me that I'm going to have an oblique asymptote at x minus 1. My asymptote is actually going to look like this. So I don't have horizontal asymptote anymore. Instead, it's oblique. My non-permissible value is still going to be x cannot be negative 1. So that shows up here. So when I go to graph this, actually, it's going to look pretty weird. My curve is going to look like this. That kind of like wonky parabola sort of effect takes place. And so we labeled our equations, and y equals x minus 1 would be the equation for that asymptote. Okay, so we get this weird oblique asymptote when we have a greater degree in the numerator than the denominator. So this kind of summarizes this idea. The graph of a rational function can have no common factors, has a horizontal asymptote at 0 if the degree in the numerator is less than the degree in the denominator. It'll have a horizontal asymptote at a specific value where a is the leading coefficient of your numerator and b is the leading coefficient of your denominator, as long as your degrees are equal. So that's what we saw in our second example here. So again, it was at 2 because it's 2 divided by 1. Leading coefficients mean your highest degree term. And finally, we get an oblique asymptote if the numerator is 1 more degree than the denominator. We're not going to deal with anything higher than that, so you don't need to worry about like if I've got like a cubic divided by a monomial or a linear equation or linear function. So based on that information, we can look at the following and just predict whether or not they have oblique asymptotes or not, and then actually go through and practice the skills that we saw in those previous examples. So quickly, using our rules, we start at the bottom and work our way up. The degree is higher than in the numerator than the denominator. And so I would predict an oblique asymptote. Okay, for example 2, again, always look at the highest exponent on your variable. So 1 here, 2 here. Because it is higher in the denominator, I'm going to double check that this doesn't cancel. This is a perfect square, so I know it won't. But you can factor it out just to make sure. Yeah, and it checks out, nothing cancels out, so I can't simplify it. So in this case, I would expect asymptote, horizontal asymptote at x equals 0, or sorry, y equals 0. So let's actually check this out. What does that look like? Well, we're going to do synthetic division here. So I'm going to switch my sign. Go 1, 6, negative 7. I'm going to expect my remainder over here. So carry down the 1. Switch. Negative 2, that's 4. 8, that's negative 15. So when I rewrite this, my simplified version, y equals x plus 4 minus 15 over x plus 2. So this piece here is what I'm going to expect as my oblique asymptote. We can drop the remainder because now I've set this up so that's always going to be a constant over my linear equation or my linear function, and so that's always going to be set up to be 0. So when we're looking at this fifth example, we see higher, so we're predicting that it would be 0. When we do our non-permissible values, we kind of bear that in mind, that nothing cancels, so still kind of keeping with that. And so there's really nothing left for us to do here because we know that this is exactly the case. If you wanted to like test out some values, you could say like as x approaches infinity, well, infinity versus infinity squared, this is going to get bigger much faster, so it would approach 0. So that's pretty much it for that one. If they're asking for the equations of these asymptotes, we've already done that. For each graph below, determine any possible NPVs, non-permissible values for x, and indicate whether it's a whole or a vertical asymptote. Determine the equations of horizontal or oblique asymptotes, and then determine the domain. So this is going to be an interesting one. Domain is exclusively linked to x, so these two kind of points go together, and then our horizontal and oblique asymptotes are going to be a little bit different, but overall, domain linked to our first point there. So first thing I look at is for my horizontal and oblique asymptotes, my numerator is a higher degree. So I would anticipate an oblique asymptote. Okay. Before I do anything though, I'm going to also rewrite this in factored form, which is x plus 4, x minus 3, x plus 3. There's no canceling here, so that's good to notice. Just kind of as a quick note, it should be plus 4 and minus 3 because of the sign on that middle term. Okay, so my non-permissible values, again, are when I set my denominator equal to 0, and I say 0 cannot be x plus 3, so x cannot be negative 3. And based on the fact that it doesn't cancel, but it is a non-permissible value, I would expect this to be a vertical asymptote. So my last piece is determining the equation of my oblique asymptote. Not my last piece, I need to state my domain. So my domain would be from negative infinity to negative 3. Oops, rounded, because it doesn't actually reach it. Asymptotes don't get crossed or have points on them. And it starts up at negative 3 on the other side and goes all the way to positive infinity. Again, that's my domain. My oblique asymptote, again, I'm going to divide this binomial into my trinomial to see if I can simplify it. So I'm going to put minus 3 and 1, 1, and negative 12. See how this pans out. We always carry down that first one. Negative 3, add them as negative 2, 6, negative 6. So my simplified version is going to be x minus 2 minus 6 over x plus 3. Remembering that this is always my horizontal asymptote, or 0. I've got the remainder of this is going to be my horizontal asymptote. And it's no longer horizontal, it's oblique. Okay, so if you want to pause this next one and give it a shot on your own, that sounds like a good idea to me. Okay, so if you paused and did this by yourself, the first thing I did again is expanded and factored out both my numerator and denominator. You'll notice I took the negative out of my denominator, and the reason that this happened is because I wanted to address the fact, oops, and this should be negative 1. Oops. There we go. I took the negative out of the denominator just so that I would have an x term first so that I could create that space for cancellation. Once I did that, I was able to identify my non-permissible values as positive and negative 1, but 1 is going to be a vertical asymptote and negative 1 is going to just be a hole because of the canceling. Thus, my domain creates quite a mouthful even when I'm using interval notation. Again, you are totally welcome to use that notation, but that's kind of your call. I personally default to the interval notation, as you know. In bearing in mind this piece here, this should be positive 2. Sorry about that. With that negative factored out, I brought it into the numerator and just distributed it through. That's what you're seeing, all these black markings over here, because I realized I'd forgotten it when I went to simplify. Because once I simplify it and cancel out those factors, this determines the shape of my graph, the remaining piece. So when I'm actually looking at for horizontal asymptotes, I'm going to look at the simplified version once I've removed my factors. So I've done that. I notice now that it's the same degree now that I've simplified it. And it was the same degree before, so that kind of was a hint. But once I've simplified it, that lets me then do my synthetic division. It lets me look at, okay, what is my coefficient, my remainder, and if you remember back from our rules way up here, if the leading coefficient for f of x and the leading coefficient for g of x in the numerator and denominator are equal, then I just take the coefficients of my numerator and denominator in my function. So if I go back down here, excuse the scrolling, coefficient here was 1, but negative, and coefficient here is 1, so I should have ended up with that negative 1. And again, that's why the black marks are in there, because I had forgotten about this negative being factored out there at some point. So there will be practice for this. The oblique asymptotes are probably the most tricky of all of them, just kind of the idea that you want to simplify them. So bear that in mind. You'll want to practice these Good luck, and as always, ask lots and lots of questions.